So white dwarf spectra are very unique signatures. If you look at this one, this graphic, the white dwarf spectra is the one in the middle, and you will see it's very, very similar to the more massive main sequence blue star below it. You will see that it has the bomber lines are prominent, but they're broadened. They're very broad compared to how narrow they are with the main sequence star. And this is because, again, of that internal pressure coming from the white dwarf because of the kinetic energy of the electrons just beneath the surface. So you have those unique, broad absorption lines. Here on the left, we have, again, the sun, the optical-only spectrum from the sun with all the absorption lines in it that we reduce to just below it, the gross cartoon barcode that only shows the major lines associated with that specific temperature of a star. And you have the image, and under the image you have the plot, the actual plot of the absorption lines, so you can calculate them so you know exactly what the wavelength is, and that will tell you the temperature. On the right-hand side, we have some spectra that are associated with some of the different types of white dwarfs, and you will see that the one in the plot and the image in the plot in the lower right-hand corner, that is a DA, a DA spectral classification white dwarf. D means it's a white dwarf. You can see from the absorption lines, they're broadened, that it would be a white dwarf, very unique. And also, it has an A designation because it has a spectra that is very similar to a Class A spectral star. Radiation laws, again, very simple relationships for stars, relationships among their area, their surface area, their temperature, their wavelength, their total output of radiation. There are three of them, and they all are dependent upon that theoretical construct. The black body radiator, the perfect black body radiator of black body is simply something that absorbs all energy that falls upon it and then reemits it all away. It doesn't gain, it doesn't lose. It takes in everything and gives everything back. And stellar surfaces, or atmospheres rather, stellar atmospheres are very good approximations of black bodies because they absorb all the radiation that's emitted from the internal parts of the star, and then they radiate it away into the interstellar medium surrounding the star. So Planck's law simply says that a hotter star emits radiation at every single wavelength across the spectrum than a cooler star. So if you look in the upper right-hand corner, you'll see the blue star emits more radiation all the way across than the cooler star, the yellow star, which emits more radiation straight across the spectrum than a cooler star. Those lines will never cross. And Wayne's law simply says that for every single star, it has a wavelength at which it produces its maximum amount of radiation, its peak wavelength of radiation. And that peak wavelength depends upon, of course, the temperature of the star. So Wayne's law is a relationship of where you can determine the temperature by using the constant and the wavelength. So you can either, if you know the temperature, you can determine the wavelength. If you know the wavelength, you can determine the temperature. And remember, some stars emit their maximum peak not in the optical part of the spectrum, but in the infrared or in the ultraviolet. It isn't always going to be in the optical part of the spectrum. The third radiation law, Stefan Boltzmann's law, simply says if you look at those curves underneath the blue star, the yellow star, the red star, if you determine the area under those curves, that area under the curve is equal to the total amount of power that is produced from that star. And that's what that relationship is. It relates the power from the star to its temperature and its surface area. Remember that you need to understand objects at all wavelengths because they look very, very different sometimes. If you look at the examples here, some of the examples from Tycho's supernova remnant, you see what it looks like in radio and infrared, in X-ray and in gamma ray. This is another infrared one, this from the WISE mission. But if I showed you an image in the optical part of the spectrum, they say there's a few tiny little pieces of fragments that are optically visible, but if I was actually to show you one, it would be absolutely nothing there. So make sure that you study these deep sky objects in different wavelengths. On the right-hand side, we have a micron SETI. We have a ground-based telescope, observation at the top, and then we have some of the first, I think these were Hubble, where you looked at Myra and saw that it had some odd little bump on it, and then the Chandra more highly resolved image that show that it actually has a white dwarf companion, and then we have the Galix ultraviolet image of Omicron SETI, or Myra, showing that it is losing material as it plows through space-time. So we still have the same basic equations and relationships. The inverse square law, of course. If you take a star and double its distance from the Earth, now the light has expanded so that the surface area it covers is 4 times. So it's only one half as bright, 1/4 as bright. If you move it 3 times away, it's 1/9. So the further away it is, it follows the inverse square law of luminosity, which is 1/r². Don't forget the simple little area, surface area, volume, because we assume everything and most everything out there is sort of a sphere. Everything, of course, is radial from the Earth. We're talking angular, so the small angular formula and radians and degrees are very important here. The simple little relationships of velocity, distance, and time, force and acceleration and mass, they hold, of course. Kepler's laws of planetary motion to help determine the mechanics of anything that's in a binary, a multiple star system. And of course, the distance modulus that we have every single year. And type 1a supernova events are important, very important as standard candles, as those cosmological yardsticks to measure distances to galaxies far, far away, because we know the absolute magnitude of a type 1a supernova event, because they, again, remember, there are differences here between 2 coalescing white dwarfs that goes type 1a supernova, or one that went type 1a supernova because of accreting too much material from a companion star. But we know the absolute brightness of that because they all have about the same mass range. It's a thermonuclear event. The maximum brightness is going to be approximately negative 19.5. So knowing that, you can plug it into the distance modulus relationship, which is a relationship between the absolute brightness, which we know for type 1As fairly closely, the apparent brightness just by looking, it allows us to calculate the distance. So the distance modulus is really important for, and it was a type 1A event that was let us know that the universe is expanding at a much greater rate than we previously had thought. We also have Hubble's law for even further away galaxies that are further away. Now, if you have a galaxy that's really far away that has a type 1a supernova event, you calculate and you can calculate its distance, and then, you know, if you've got something sort of not too different than in distance from us than that, you can apply Hubble's law because you know the distance from the distance modulus, and it's just another way, a second way to determine if your calculations are correct. If you have if you get two different answers with two different techniques, and they are compatible with each other. Remember, I do believe they still think Hubble's constant is 70 kilometers per second per megaparsec. I know there's been a lot of different constants given out. I think it's still that. But basically, no matter where you are in the universe, your perspective tells you that every single thing in the universe is moving away from you in every direction. And the further it is, the faster the rate of expansion. And Hubble's law will give you an idea of the recessional velocity of those galaxies.